Markus Klute. He was born in Germany and then studied in Bonn, and then spent already some time in his doctoral studies in CERN, in Switzerland, and also in Fermilab in the US, close to Chicago. And then after completing his doctorate in 2004, he moved to work as a researcher to Massachusetts Institute of Technology in Cambridge in the US, it's Boston. And then became their professor, first assistant professor, then associate professor, and in 2020, full professor. In between, there was a short stop in Göttingen, only 1 year, or about that time, from 2008 to 2009. But it's really great that Humboldt Foundation succeeded to get him back, and at KT we are extremely proud of him joining the faculty. Markus Klute and his team played a significant role in discovering Higgs boson. In this experiment, which was performed in CERN in 2012, or at least was reported in 2012, this was a really great event in physics. It was a spectacular moment in basic research to confirm the last missing block of the standard model, which is the foundation of the construction of our world, of the particle physics. And he's specifically working on the called CMS experiment. This is a Compact Muon Solenoid experiment. Between other contributions, his group also played a great role in employing modern machine learning techniques in the high energy physics. And at KT, we are actually extremely proud and happy him being here, because this also introduces a new era of working in the field of high energy physics and continue research in Large Hadron Collider in CERN, where more precise measurements and pathbreaking experiments are to be done in the plans of the next decade at least, or beyond. So thank you for taking time to speak at this day, and I'm looking forward to your talk.
The title of the talk is Unveiling Nature's Secrets, the Future of Particle Physics, and that's a very broad title, and I will talk about an aspect of particle physics, not all of particle physics. So what is particle physics about? Particle physics is a field of physics where we deal with elementary particles. So we want to understand what are those particles, what kind of particles are there, what are their properties, how do they interact, really on the very fundamental level. And while this field of physics, the theory can be described as a quantum field theory, the number of constituents and the number of interactions is actually quite limited. So those are all the particles we know, and their interactions are summarized in this very simple plot. In the inner part, you find the Higgs boson. We already heard 10 years ago we discovered a new particle, and the role of this particle and the mechanism associated to this is to give mass to elementary particles. Then there is basically three interactions: the electromagnetic, the weak, and the strong interaction. And you're all familiar with this. The weak bosons are super important for the sun to burn, for example, or in beta decays. And the gluon is a particle which glues together the other fundamental particles, quarks to protons, for example. So our model here, the standard model, is our best. It's actually not just the model, it's a theory which describes those properties, interactions of elementary particles. The really special thing about the standard model in particle physics is that this theory is highly predictive. We can use this theory in order to make a forecast of the outcome of an experiment, or we can confront the data with the theory directly. And in doing so, it's extremely successful. We have done many experiments. We have tested the standard model in many different regimes, in many scales of energy. And we don't find significant deviations of our experiments with this theory. So it works. It's fantastic. But there's also a shortcoming. This model, or the standard model, doesn't describe very fundamental things about nature. For example, fundamental parameters like the masses of those particles. They are parameters. We don't know why they are the way they are. We don't know what drives them and where they're coming from. And there's also really fundamental phenomena which we cannot explain, and one of them is dark matter. And I'll talk a little bit more about this, but also the asymmetry between matter and antimatter. When we look out in the universe, and we're doing this with experiments, we don't see much. We see some antimatter, but not much. So the universe is dominated by matter. while the mechanisms which leads to asymmetry between matter and antimatter, they're quite limited. They don't give us, the universe we actually live in. So there is something missing in our understanding. So one of the questions which fascinates me still, is this table here. So this is the same particle we just discussed. Now I'm listing them as what we call families. So we just list them ordered by mass and their properties, and you find some of them, the up quark and the down quark and the electron. Those are fundamental particles you find, in this table here, for example. Those are the particles which surround us every day. And then there's heavier brothers and sisters, like the muon and heavier quarks, which we typically produce, in cosmic radiation or in experiments. And what's fascinating about this is, even though we don't have a mechanism which makes those masses very different, they are very different. This is a logarithmic scale. So the difference in masses, for example, the top quark as the heaviest elementary particle is as heavy as a gold atom, while, orders of magnitude lighter is than the electron, the particle which governs the structure of atoms. And then there is a line, because there's many other order of magnitude to particles which are also fundamental, which are neutrinos. So understanding the mechanism which actually gives those particle mass is something which to some level is succeeded in through the Higgs mechanism by the discovery of this particle. But really understanding what drives those parameters, we don't really know. It's again on this book, we have no idea. We don't know. If you, for example, take the up quark and the down quark, flip the order in their masses and just assign a mass to one of the other, you'll find that a proton wouldn't be a stable particle anymore and the universe wouldn't exist. Right? Or the electron, for example. The mass of the electron governs the size of an atom, and with that, chemistry. So everything you see around here is depending on the mass of the electron to some level, because that drives chemical reactions in the strength of the interaction. So those are really fundamental to us being here, I would argue. Nevertheless, we don't understand why they have the values they have. So this is an interesting question. Okay, if we step back one step further, ask what is mass and what is the universe, what does the universe consist of? You can start with some bean counting. You can ask how much matter is there in the universe? And we find that the matter we actually understand, something like this table, is only a very small fraction of the energy mass in the universe, about 5%. Most of the energy is something which is called dark energy, and we don't know really what that is. Matter, things, some things we might, be able to understand through gravitational effects. Dark matter still is a much larger fraction of the matter in the universe, about 25% of the total. Okay, so most of this energy and matter in the universe we don't really understand. So that, again, I'm trying to make the point that there is a lot of interesting open questions where the answer currently is we have no idea. Okay? So if you look at the atoms, the 5%, and ask, what is there out there in the universe? The answer is it's mostly hydrogen. It's mostly a proton with an electron around this, and there's some helium and a few more heavier elements. So we are actually in a quite special place when we look around this. There's a lot of carbon and oxygen and nitrogen and so on. The universe doesn't look like this. So this planet here is a very special place. Hydrogen is basically a proton, and we do understand what the proton is being made of. The proton is two quarks, two up quarks and a down quark, and in the little less naive picture, those quarks interact via gluon. So the gluon holds them together, and if you look a little bit more precisely, you see a few other quarks and antiquarks as part of this proton. So this mass, this 5%, is basically built by the mass of the proton in some units, 1 GeV about, or 900 MeV. If you try to add up the masses of the constituents, you find this is not really accounting. The mass doesn't really add up. Those quarks are much lighter, and the sum of the quark much lighter than the mass of the proton. What really happens here is that the kinetic energy of the quarks and the energy stored in the fields holding them together gives dynamically the mass to the proton, okay? And therefore the mass, the visible mass of the universe, okay? And we have tested this. You can actually calculate then the mass of particles similar to the proton, and this is shown in this little table there, where you can forecast and calculate using techniques we have developed over the year, the mass of other particles. And so this theory works. So we do understand this 5% quite well. and the 5% is not dominated by the mass of the quarks. The big next question is, however, what is dark matter? Out there in the universe, what is it made of? Does it have any sort of structure, anything we can understand with elementary particles? And we know about dark matter for a long time. We know about dark matter through gravitational effects. We can study the rotation of stars in a galaxy. We can study the bending of light through matter, so gravitational effects. And all of this points to the existence of dark matter. So we are quite confident that dark matter exists, very confident that dark matter exists, but we don't know what it is. We are not short of ideas, though. So this is just a nice picture which summarizes a little bit, what kind of spectrum of ideas there are which could explain dark matter. And so this is by Tim Trade, a colleague, and supersymmetry here developed in Karlsruhe up there in this building is one of the series of theoretical ideas which gives candidates for dark matter. The issue is we haven't discovered supersymmetry or the dark matter candidate, and there's many others, axions. There's exotic ones with extra dimensions, little Higgs, littlest Higgs, axion-like particles, and interesting names occur in this spectrum. So we're not short of ideas. Still, over the many years, we were not able to discover dark matter. And the reason is, and this is kind of a circular argument to some degree, the reason is that where we look, dark matter doesn't exist. So we were able to look and explore, but we haven't discovered. This is probably the most difficult plot in this talk, and it shows on these two axes two things. One is a mass of this hypothetical particle, so how heavy the particle is, and on this axis, how likely the interaction of this particle is with ordinary matter. And our experiments work in such a way that we have ordinary matter and we look for interactions with this dark matter, at least some of the experiments. And what you see is that we can probe a specific mass rate up in this corner, and we can probe the interaction rate to some level, but not further. And that the reason for this is that our experiments need to grow in size, or we need to collect data for a longer period of time, or we need to develop new machines which allow us to create new particles at higher energies. So I've drawn 3 arrows here, which means that in order to explore this question further, ways to do this is by creating machines which allow the creation of heavier particles. We have to make bigger experiments in order to have more material there which can interact with dark matter, and we have to have new ideas which allow us to go to lighter and lighter particles. This is one plot. I could have taken many plots which have all this similar spectrum. So we have looked, we haven't observed this, and the next step is to have new ideas, new technologies in order to explore the phase space which we haven't looked at yet. So the charge for us is to keep exploring and to figure out what dark matter might be. We accelerate and collide particles at the highest energies. So naively you say we go to the higher energy part, we push the knowledge in one direction, but we also do this in higher intensities, so we also try to have higher interaction rates. So we study particle interactions, resulting products and features, and by that learn about the interactions. And we do this at higher energies for a number of reasons. We want to look deeper into the structure of matter. We want to create matter at really high temperatures to study, how does the matter behave when you have it really hot, like in the early universe. And then the thing you're probably very familiar with is E equals mc squared. Everybody has seen this equation before. We try to generate or create heavier particles, potential particles which help us understand what lays beyond our current knowledge. And in the collider physics world, we all do this in a very controlled environment. We can repeat experiments, we can control the behavior and the setup of what we study. Okay, so what we need is powerful machines, accelerators, to accelerate particles to extremely high energies. We need detectors, so we need cameras which look at the collisions and what's the outcome of those collisions. And then we also need a lot of computing because we generate so much data which we need to store and we need to reconstruct and analyze. We also, because our theory is very predictive, we have the ability to simulate the outcome of the experiment with much detail. So we can mimic an experiment without even running it. And that's quite interesting just to compare the collected data with the simulation, but it also allows us to explore the next generation of experiments before actually building it. And then we need a lot of people. scientists, engineers to design, build, operate those complex machines, and we need physicists to extract the physics from all of this. It's about 3,000 physicists, 1,000 engineers, technicians. Fascinating number is this is 240 institutions out of 54 countries. Also, the number of PhD students is quite fascinating. 2,000 PhD physicists are involved in 1,000 postdoctoral students. So it's very large. It's interesting as a construct by itself, and it's extremely international. So you find people from all over this planet participating in this kind of research. The accelerator itself is also very large, and its name already carries this, right? The Large Hadron Collider. This is the accelerator which allows us to produce particle collisions at the highest energies, and at that collider there is in principle 4 big experiments, CMS and ATLAS. We call them sometimes omni-purpose experiments. There is a large spectrum of physics we can do with those experiments. And then there's ALICE and LHCb, who are more dedicated experiments which have a larger but more targeted physics goal. As a comparison, this is the aircraft accelerator there on the side in Geneva. The airport, the runway is probably about 3 kilometers long. This is large. CMS is actually in France. ATLAS is in Switzerland. The ring is actually about 100 meters under the surface. So when you fly over Geneva, you don't see much of this. You might see a few surface buildings, but the ring is underground. And what we do with this ring is we accelerate protons. So we start with this hydrogen. We strip off an electron so it's charged. And then we accelerate those protons. And we don't do this one by one. We basically have bunches of them. In each bund there's 10 to the 11 protons. So in a beam of protons, there is, in the collision, 10 to the 14 protons colliding with 10 to the 14 protons. The rate of collision is 40 megahertz. So the actual rate of proton-proton collision is in the order of a gigahertz. So that's a very large number, but within those bunches of protons, then there's individual protons, and the collisions we're interested in are actually the collisions of the partons, those quarks or gluons within the proton. And then we surround this interaction point with our detectors, with our cameras, and we take pictures. Why do we need so many of those protons? This is not an easy plot, but I hope I'm able to explain it. So this, what is called cross-section here, is actually the likelihood of something specific to occur in a given proton-proton collision in some units. And so the likelihood that there's something happening is given here. It's a very large number. On average, in 1 in 10 to the 11 proton-proton collision, we produce a Higgs boson. And that tells you why we need so many of those collisions to study the Higgs boson with precision. Other physics down here, especially those at higher mass scale, they are even less likely to occur. So we need more of those collisions in order to have sensitivity to find this hypothetical new physics. That explains to you why we continue to run, and we continue to run even at higher intensities, because we have interest in finding this kind of potential new physics. All right, and this is the experiment, the CMS experiment as an example. We sometimes say this is a typical particle physics experiment, but there's nothing typical about it. Just the overall idea and concept is typical. So what we do is, this is a synchronous camera, so we take those pictures 40 million times per second. There's about 100 million channels in this camera, and the shutter speed is 40 megahertz, right? So we constantly take data, but we are not interested in most of it. So we have already in the electronics and later in computing system, a built-in system where we basically only record or only analyze about 1,000 events, maybe 2,000 events per second. Those which might give us some insight about the Higgs boson or other new physics. The structure of this detector is such that in the inner part we want to not disturb the particles which come out of the collisions, but we still want to measure them. And we do this with, in this case, silicon technology. So there's a silicon detector, charged particles fly through like an electron, and it does a little bit of ionization, and we can then amplify the signal and figure out, there was a particle. And then a little later there was the same particle, and then we connect those to a track. We put this all in a magnetic field, a compact muon solenoid. The solenoid is the magnet. CMS stands for compact muon solenoid. So this magnet here is a superconducting magnet. It's the world's biggest magnet in terms of stored energy. It's just very, very big and has a field strength of 3.8 Tesla. And we use the magnet in order to bend charged particle in a curvature, and so that curvature then tells us the momentum of the particle. And then we just try to stop everybody. And we use calorimeters for this. This is heavy material. For example, lead tungsten, those are lead crystals. They're transparent. Particles go in, they shower, they make photons, and at the end we collect the number of photons, which is a measure of the energy. So we try to stop everybody, and some particles that don't want to cooperate, they just basically fly through. One type of particles are so-called muons. They only leave a little bit of energy, so they can be detected outside here again. And neutrinos, they just fly through. Their interaction length, they can go through a light year of lead, and with minimal impact. And so those we don't measure really. And dark matter we would also not measure. So dark matter candidates, they look exactly like neutrinos in this kind of experiments. Okay. Coming already to the end, or to the day, the legacy of the LHC so far, so this is a running experiment or running accelerator, is that we discovered this new particle. And so at the time, in July 4th, 2012, we celebrated this with an event at CERN. There was a press release. At the same time, we had a big international conference in Melbourne where we actually presented the result and discussed them with everybody else in the field. So this was fantastic. And since then, if you want to summarize in one plot what we learned since then, this is the plot. And so what's plotted here is the particle mass of the particles you saw in the beginning, some of them, and the coupling to the Higgs field. And what you see is that we were able to draw a line through those points. And what this means is that there's a relation between the coupling of the particle to the Higgs and their masses. Now, turn this around. The understanding we have how, for example, a muon becomes massive is that it interacts with the Higgs field. And that interaction gives it some sort of inertia, and that inertia is its mass. So the stronger the particle couples to the field, the heavier it is. And that's exactly what you see in this line. Some of the particles, for the lighter particles, we did not, because the rate of interaction is so low that it's very difficult to observe this. But there's another legacy to this. The legacy I'm extremely proud of is that I'm part of this international collaboration. That bringing all those people together with a common goal and achieving something as big as this accelerator, as the collaboration, the machines, the detectors, and working together on this common question. I think this is an extreme success. And this is not just bringing the people together, but it's also a scientific success in that those large collaborations, they're kind of big companies where we have inputs of people and money and resources and knowledge. We just work together on those questions and put it all together. And it has been successful, and I'm pretty sure it's going to stay successful, even if there's all kinds of challenges out in the world. And the other thing I'm very proud of is that even in the discovery of the Higgs boson, we used modern machine learning techniques, neural networks, and other techniques in order to extract as much information from the collisions, from the data we collect as possible. So we try to use the data which is recorded by the detector to its fullest, and the way we do this is by using machine learning techniques in order to separate signals from background, but also to reconstruct certain elements of particle signatures in the detector and so on. Hopefully able to show you that it's big in number of people, that it's big in number of the size of the experiment, but there's another dimension, that's time. So this is the current schedule as we understand it for the LHC to look forward. We're just coming out of what we call a shutdown. And in green here are periods in which we actually want to run and operate the accelerator and the detectors. So we're just starting, July 5th is the day when we actually want to start, with the next run, with the next accumulation of data. And the plan is to do this for 4 years, and then we stop again, we refurbish the detectors in the machine, and then we do this again, and then we do this again till 2038. That's the current plan, and if I would have to make a bet, there's another run afterwards. We want to fully exploit the machine, and in order to actually make scientific progress in a human scalable way, we increase the intensity, so we take more and more data, and more quickly we take this data. And there's another part to this. This is not a machine we just built. The first workshop which discussed the Large Hadron Collider was in 1984. The first collisions were recorded in 2009, and we spent the last 10 or 15 years exploring the first one and the second one with the discovery of the Higgs boson and the measurement I just showed you. So this is a human lifetime, right? So this is a scientific career in this. So why do I show this to you? Because we're also planning the future beyond the LHC. And so before I talk about this, I want to tell you a little bit about the life cycle of a particle physics experiment. So it all starts with an idea or physics question, some theory idea, maybe Ulrich Nierste in the back has some idea for a new measurement, and then we experimentalists, we think, and how can we actually study this, right? And so then we start this with sensitivity studies. So we use simulation in order to figure out if the experiment would actually work, has a sensitivity to answer the question. Then we often have to do a lot of research and development of new technologies in order to make this step forward in experimentation. Then there is a phase of construction and commissioning, which is then followed by data taking. We have to manage the data, we have to analyze the data and ask, what does it all mean? Right? And that's a dialogue, a constant dialogue. So there's a lot of technology development in there and large-scale instrumentation, but there's also the aspect of modern computing analysis, and then obviously the physics insight into this. And for some experiments, this is a cycle which is a couple of years, and you just saw the life cycle for the LHC. What I didn't tell you in this is that we go around this cycle a few times, even with the same experiment. And this is shown here. So this is me here at the day where we turned on the magnet at CMS. We are just in this commissioning phase, so we have updated some of the component of the detector, also of the machine, and we're just restarting for the next run. And so we were super excited to have the first beam at the highest energy, just a little bit higher than before. And so the first stable beam where we have actual collision is then planned for July 5th. So in the next shutdown, in the next pause, we want to majorly refurbish the detector, and you don't have to read any of this. The point of the slide is that there's a lot of things we have to touch with the detector in order to make it ready to have intensities of the LHC which are about 5 to 6 or 7 times larger than we have today. And KIT is heavily involved in replacing the heart of the detector, which is the tracking, the silicon tracker, and we're also involved in building part of a forward calorimeter here. Currently those are the SLED crystals, and we have a new technology we would like to put in there. So this is all happening at the same time, and it's extremely fascinating to be able to analyze the data, to build the next detector, and then to think about the next machine afterwards, right? So if your 38 is not long enough, or 40-something is not long enough, the question is, what do we do afterwards, or how do we actually make the next step? So clearly the LHC is the energy frontier for me at least, foreseeable future. The question is, how do we make significant progress in our understanding beyond what we expect to learn from the LHC? And so we have agreed as a particle physics community that the Higgs boson, understanding this to yet another level, is one of the key questions. And for that, we have to build a new machine. And so what this new machine is up for discussion still. There's a lot of proposals. They all have acronyms or names. And the one I'm involved in is called Future Circular. And as for the LHC, we haven't started yesterday discussing this. We actually started before this FCC, Future Circular study. When we discovered the Higgs boson, I had a meeting a week later when I came back from Melbourne discussing how this machine might look like. So we knew we had discovered this particle, and we knew there's limitations to what we can learn about this particle at the LHC. And the answer, one of the answers, is a machine like this. So first of all, what you see is a big ring. And in this big ring, we can, at the LHC, collide protons with proton. But what's actually smarter or more efficient to study the Higgs boson is to collide electrons with positrons, because those are elementary particles, and they allow more precise data and more precise analysis in order to study the Higgs boson. And again, the timeline, right? So we have a plan for this. So we're currently in what we call a feasibility study. That has to do with some of, how we would build a detector, what is the physics reach, but much more important and out of my scope, what does it take to build a tunnel like this, right? And can we finance it somehow? Yeah. That's a really important question in this. And we give ourselves some time for this, a few more years, and then we come back together as a community, we discuss again, and if we all are convinced that we can do it and that we want to do it, then we might start building this 2030. And then for 10 years, nothing happens but civil construction. So it takes a while to build a large facility like this. The operation would be a couple of years, a few years of operation of an electron-positron collider, and later then we would be able to use proton-proton collisions again. And those proton-proton collisions would not be at 13 tera-electron volts, but almost 100 tera-electron volts. And again, in order to make this possible, we have to develop new technologies, specifically new magnets which bend the proton on this tiny circle. Okay, I love this quote. So Sam Ting is a colleague of mine at MIT. He won a Nobel Prize for the discovery of a particle in the 70s and has been a leader in lepton collider physics, and is also responsible for an experiment, the only particle physics experiment on the International Space Station. Fantastic. And so he said every event at a lepton collider is physics, every event at a hadron collider is background. And that's not quite true. As I was explaining, those hadron collider events, they can lead to precision studies of the Higgs boson. So I like to, use George Orwell a little bit more. All events are equal, some are more equal than others. And the reason is that the electron and electron colliders, electron-positron collider and the proton-proton collider, they're actually quite complementary. You can learn interesting things from one or the others. Those proton-proton machines, we have learned, they can be precision machines, but they're also able to go to really high energies. And therefore, they're complementary to an electron-positron collider, was really dedicated not to go to so high energies, but for precision measurements. So we studied this, and so now with this machine, with both of those machines, electron-positron collisions and proton-proton collisions, we can ask, what is the key leading questions? And one here is, for example, what are candidates for dark matter, the nature of the Higgs boson, the origin of QCD. Those are all interesting leading physics questions in particle physics. And for most of them, you can answer those questions best in comparison to other machines, part of those proposals with FCC. And in some cases, it's the plus or minus machine, and in other cases, it's a proton-proton machine. And in combination, the answer is in most the best you can do. So that's kind of my selling point for this machine. All right. So if you haven't learned enough about the Higgs boson in this talk, this is a little bit of an advertisement here. We're actually celebrating the 10-year of the discovery, not just at CERN. There's a day-long symposium on, where people remember what happened in July 4th, 2012, but there's also physics discussions about the current state of the art of this physics. But here in Karlsruhe, we want to have a party. And so what we do is first, we have a public event where we'll talk a little bit about this story of the discovery and what we learned from this. And then we have a podium discussion here with faculty in the physics department, talking about what I just talked about. What is a possible future in particle physics, and what do we want to do and learn about nature this way. So this is one event, July 4th, in the Gerzen-Hörsaal. It's just down there. And then we have a almost month-long event in the Triangle, which is at the Kronenplatz here, where in the afternoons you can learn about all kinds of physics, particle physics, and talk to colleagues of us. And one I want to highlight here on the 29th of July, we will discuss what we do with the Higgs boson. But it's almost every afternoon. The program is available, and we will distribute flyers for this as well. So I hope this is going to be a lot of fun. All right, so a few concluding remarks. So first of all, after the discovery of the Higgs boson, the question was, what's next? And so the immediate question for me after the discovery, is this really the Higgs boson? What can we learn about this? Does the Higgs boson couple to those electron-like particles, and so on? And many of those questions we have answered. The real next question for me is really dark matter. And dark matter can be studied with the machine I just described, but also with much smaller experiments. But it's actually quite difficult to predict, especially the future. So it's not clear how the field will develop, whether or not we will be able to build such a big machine or even the small experiments. But I'm sure that the progress will come through technology and new ideas. The data will reveal how nature actually, nature's secrets, and how nature actually can be described. Those different machines, they are complementary, and there's complementary approaches, not just the electron and the proton colliders, but also the big machines compared to smaller experiments and more dedicated experiments. It's important to continue to innovate and to some level also invest in order to make this progress and those advances in technology. And so sometimes I'm getting asked, what if you don't find anything? And so my spirit is here really one of exploration. You know, if we don't look, we will not find. And clearly, it's really a fun process we are going through. I mean, especially when you combine the development of new technologies, which are sometimes used in other areas of humanity as well, but really trying to learn about the fundamental interactions of how the universe is put together. That's really what I'm after. Thank you.
Great. So I think we are exactly on schedule now. It's 5 p.m. and I think we really enjoyed the talk a lot. Thank you.